The next example for finding the vapor pressure of a solution will involve an ionic non-volatile solute. So because the solute is non-volatile, it means it's not going to create a vapor pressure, and the only thing that's going to be creating vapor pressure in our solution is the solvent. Raoult's law says that we expect the vapor pressure of our solvent to decrease as we're dissolving things into it, and so this is something that we're going to check later on. So our non-volatile solute means it's not going to create a vapor pressure on its own, so all we have to do is look at the vapor pressure of the solvent going into the vapor pressure of the solution. The big difference here now is because the solute is ionic, we need to take into account that that solute is going to dissociate into multiple species. So we need to include the Van't Hoff factor I inside of our calculations somewhere. So we're going to see that. Examples of ionic non-volatile solutes are salts like NaCl and NaOH, and we know that these, when they dissolve in water, are going to dissociate to make multiple species. So like NaCl is going to dissociate to make Na plus and Cl minus, so its I value is going to be equal to 2. So the main thing we're looking at here, because our solute is ionic, we need to include I somewhere inside of our calculation. We are still using Raoult's law, and Raoult's law says that the vapor pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. But where I is going to show up is in the calculation for our mole fraction. Here I've given you an example. We're still using about 100 grams of water. And remember, because we're looking at a mole fraction, what we need is moles of our solute and moles of our solvent. So we have 100 grams of water. Water is our solvent. That's equal to 5.56 moles of water. Our solute, in this case, NaCl, is we're putting 11.7 grams, and that's equal to 0.200 moles of NaCl. We have our vapor pressure of our pure solvent at the temperature that we are interested in, and just like before, we're going to use Raoult's law. What we need from Raoult's law is the mole fraction of the solvent. So remember, we're looking for the mole fraction of the solvent here. That's going to be equal to moles of water divided by moles total. And moles total are going to be equal to the moles of the solute plus the moles of the solvent. And water is our solvent, NaCl is our solute. But we need to consider the fact that NaCl dissociates to make more than one species. It goes to make Na plus and Cl minus. So NaCl has an I factor of 2. So when you look at the mole fraction, that's moles of water divided by the summation of the moles of NaCl plus the moles of water, but we multiply the moles of NaCl times our I factor. So we need to include that in there, that as NaCl dissociates, it's going to make 2 species. So the I factor shows up inside of the mole fraction, and it's going to have an overall effect on our calculations. So when we do the calculation, we had 5.56 moles of water, and we divide that by our moles of NaCl multiplied by its I factor 2 plus the number of moles of water in itself. So when we do this calculation, the moles of water is here our adjusted total number of moles. So it's really not the total number of moles because we've included an I factor here, but it's the effective number of moles. We multiply that by the vapor pressure of pure water, which was given here. And overall, we calculate a new vapor pressure for our solution. And at the end, we want to take a second and make sure we expect the vapor pressure of our solvent to be higher than the vapor pressure of our solution. So that has occurred, and that's something that we expected.